Most residents think their linear accelerator is like a magic box. You sit at the console, you press a button, and magically radiation comes out. But if you do not know exactly how that beam is created, you have absolutely no business prescribing it. Today, we will break that myth. We are going deep inside and look at an important machine, the X-ray tube. This X-ray tube is required to produce X-rays. Do you have any idea what actually happens inside that glass envelope? It is not magic. It is pure controlled physical violence. Yes, it is literally a physical violence. We are vigorously boiling off electrons at thousands of degrees. We are accelerating them to unimaginable speeds across a complete zero atmosphere vacuum. And then we are smashing them into a solid piece of tungsten. But here is the most shocking part of this entire process. 99% of that massive energy released due to this collision is completely wasted. It instantly turns into extreme heat. Only 1%, just 1% becomes an actual X-ray photon beam we used to destroy cancer DNA. How does the machine survive that extreme heat without melting down? How do we control that chaotic collision to produce a precise, life-saving beam? If you want to master radiation oncology, you cannot just memorize clinical guidelines. You must fundamentally understand the X-ray photons. Pay very close attention to this lecture because today we are diving deep into the X-ray tube. Hello friends. Before we begin, for those who are new to this channel, I am Dr. Parveen Ahlawat. I am a consultant at Rajiv Gandhi Cancer Institute and Research Center in New Delhi for over 12 years. I have been practicing and teaching oncology for more than a decade. I did my MBBS and post-graduation from CMC Vellore. Then I did my DNB at Rajiv Gandhi Cancer Institute and Research Center, New Delhi. I pursued a fellowship at the Royal Marsden Hospital in London and have later undergone specialized training in cyberknife from the United States. I have published almost 85 research articles and abstracts in PubMed Index international journals. Hello friends. Welcome back to our series of lectures on radiation physics. In our previous session, we looked at the atom. We learned about binding energy. We discovered that we need a large amount of external energy to eject an electron from its orbit. But we also realized that we need a machine to fire high-speed electrons at the atom. Today we will look at that machine. This is an X-ray tube. It is the heart of your radiology department. See the sequence of events here. You can see the cathode having a heated filament. This filament produces a large amount of electrons. These electrons are accelerated to a very high speed. They fly across the empty glass tube. Then they smash into this heavy tungsten target. This target is mounted on the copper anode on the right side. What happens during this massive collision? Most of the energy is lost. More than 99% of energy produced is lost as heat. Only less than 1% survive. It is this tiny 1% energy which becomes the actual X-ray photons. This 1% is actual clinical X-ray beam we use to treat cancer. Today I will teach you exactly how this tube works. We will see exactly how these X-rays are produced. Let us begin. This is a real photo of a man holding an X-ray tube. This is how an X-ray tube looks like. This gives you a very good idea of its relative real physical size. You notice that it is a pretty much simple machine. These are various pictures of actual real X-ray tubes. They all look slightly different in sizes and shape, but the basic structure remains same. And we will see its component in the next slide. These pictures show you exactly how these tubes look from different vendors. Look at the white machine in the right lower corner. This is the most recent and modern design X-ray tube we have these days. This is exactly what is kept inside our modern X-ray diagnostic machines today. Now listen, you might wonder where all these X-ray tubes are located in our hospital. You have been walking around the hospital since many years, but have you ever seen any signboard showing X-ray tube? Where are they located? They are actually the core radiology machines in your radiology department. You will find them inside your all standard radiography machines. The chest X-ray you get, bone X-ray you get are all taken from that diagnostic X-ray machine in your radiology department. They are the heart of our CT scan machines also, and our mammography machines also. You will also see them inside fluoroscopy machine used in cath lab and operation theater rooms. They are even inside the portable X-ray units we rush to the ICU or emergency room every now and then. So basically, X-ray tubes are the workhorse of any radiology department. Literally, radiology means X-ray tubes. But let me ask you this question. How about your own specialization? Do you, as a radiation oncologist, use X-ray tubes? Are these X-ray tubes located in your radiation oncology department also? Have you ever seen them? No? Yes, you use it every single day and many a times a day. Shocked? Can you recall now where and how often you use X-ray tubes? Listen to me very carefully. Most radiation oncology residents make a massive fundamental mistake. They think X-ray tube belong only to radiology department. They think I am a radiation oncologist. I have nothing to do with X-ray tubes. Why should I waste my time learning about X-ray tube? Let me break that myth for you right now. Let me give you a shock. There are actually X-ray tube hidden right inside your own department. Where are they? Number 1, your CT simulator. Every time you acquire CT scans for your radiation planning, you are actually using an X-ray tube. Number 2, your conventional 2D simulator. If your department has this machine, it uses an X-ray tube combined with fluoroscopy to take orthogonal images and mark your conventional treatment border. But now let me give you a shock again. Let me tell you about another ultimate place where this X-ray tube is kept in your department. A place you look at every single day but probably never realized. Your linear accelerator. See this image. A patient is lying on the treatment couch. Do you see that vertical line light brown beam firing from the main gantry positioned at 0 degree? This is your main megavoltage radiation system. That is the therapeutic X-ray beam you use to kill the tumor. I am not talking about this. But now look very, very carefully. Look exactly 90 degrees away from that main beam. Look at that separate arm hanging off the side, that C arm. Inside that arm sits a standard diagnostic X-ray tube. It is exactly like the ones used in the radiology department. And it is firing that green beam you see on your screen. This is your onboard imager, in short OBI. You use this exact X-ray tube every single day to take your orthogonal 2D images. You also use it every single day to take your CBCT, cone beam CT scans. You rely on this tube for all of your image-guided radiotherapy. Do not ever make the mistake of thinking you do not need to understand the X-ray tube. You use it every single day on your patients. If you do not understand exactly how this X-ray tube works, you do not truly understand your own linear accelerator. Let us understand this. Before that, you might ask why we should infiltrate the radiology department to look at that equipment. Look at their equipments. We as radiation oncologists already have a big machine, linear accelerator, to learn. You might easily feel that this is a distraction from your main clinical training. But understanding the simple functioning of X-ray tube is definitely not a waste of your time. It gives you the absolute core physics you need to master your entire radiation physics. Look at the pyramidal diagram on your screen. Understanding this simple X-ray tube forms the absolute foundation of all radiation physics. Everything you need to know about radiation physics starts right here at the base. If you do not spend time now to understand the X-ray tube, you simply will not develop a good foundation of radiation physics. Without this solid base, the entire clinical structure above it will eventually collapse. Today we are going to look deep inside this X-ray tube. Let us begin. What does X-ray tubes do? They are required to produce X-rays. There are three requirements, or you can say prerequisites, for X-ray production to happen. All three must be met. First, there should be a source of electrons which produces electrons. Second, these electrons should be accelerated. Third, electrons should finally be decelerated or stopped suddenly. If you do not have any of these three, you cannot create X-rays. Here is the important thing. Listen carefully. When all three requirements for X-ray production are met, there occurs a violent impact. This impact results in the birth of two types of X-ray radiation. The first is the continuous spectrum of Bremsstrahlung X-rays or radiation. The second is the discrete energy of characteristics X-ray or radiation. These are the absolute basics that every single radiation oncology resident must completely master. I will explain you these two important X-rays in my next video. Don't worry about what is happening with the electrons and orbit here in this image. Today we will focus on X-ray tube and how it produces X-rays. I will now show you exactly how the inside of an X-ray tube looks like and how it works. I will teach you these basics today. So please stay with me. This is how an actual X-ray tube looks like. This is exactly what the device looks like in real life. Notice there is a large transparent glass envelope that protects all the internal parts of this X-ray tube. This entire glass bulb is highly evacuated. All the air is evacuated from this glass envelope so that the electrons can travel safely without hitting any air molecules inside the tube. If you look at the left side of the image, you can see several colored wires. These wires basically provide the electrical connections to the negative cathode. Now look at the right side within this tube. Here, you can clearly see a heavy and thick metallic plate in the form of a disc. This is our positive anode. It contains the heavy copper components and the target where the X-rays are actually produced. Now look outside the X-ray tube on the right side. You can see these thick bundles of copper wires. You might wonder what these heavy copper wires are doing here in an X-ray tube. The entire part is essentially a very powerful motor. It uses strong magnets to rapidly spin this heavy anode target. Why do we need the anode target to spin fast? Because understand that the production of X-ray generates a massive amount of heat. In fact, more than 99% of the energy while producing X-ray is wasted as pure heat. Only less than 1% actually becomes useful X-ray. If the high-speed electrons keep hitting one single stationary spot continuously, that intense heat will quickly melt and destroy the target. The solution to this is make anodes spinning continuously so that the electrons do not strike a particular point all the time. They strike a continuously revolving track. This beautifully spreads the intense heat over a much larger surface area. And to spin this anode, we need this motor. This simple spinning design protects our X-ray tube from melting and greatly extends its life. So this is how an X-ray tube looks from outside. Now let us go inside this tube and see how these parts work together to create X-ray radiation. Now see, this is a very nice setup showing the entire X-ray tube. I will spend a lot of time on this slide to explain you about this entire setup of X-ray tube. Let us look inside the glass envelope to understand the internal structure. It consists of a glass envelope with a very high vacuum inside it. We don't want any air in this envelope. The pressure inside this vacuum chamber is strictly maintained at 10 to the power of minus 6 millimeter of mercury. This extreme vacuum is very important so that electrons can travel without hitting any air molecules. On the left side, you are seeing the negative electrode. Let us turn it and zoom here to see what is there in it. This is the cathode. This golden color coiled filament. Cathode is a simple tungsten filament. The filament there in cathode is directly connected to a small low tension battery. Notice that the filament is carefully surrounded by a white metallic structure, this one. This is the molybdenum cylinder. This is called as focusing cup. It is kept at a negative voltage compared to the filament. Very important. it is kept at a negative voltage compared to the filament. Because electrons are negatively charged, the negative charge created at the molybdenum cylinder strongly repels the electrons. It forces the electron to form a very fine pencil beam at the center of the cylinder. We will see that fine pencil beam of electrons in next slide. Now look at the center of the diagram. You are seeing the positive electrode here. This white color. This is called anode. Anode. Anode contains the target material. The target is made up of a metal with a high atomic weight. The target is generally made of a small piece of tungsten. Tungsten, remember this. This target is securely embedded directly into a large thick copper block. See this brown color thick block. There are two very important reasons why we strictly choose tungsten as our target material. First, tungsten has a very high atomic number of 74. This high atomic number significantly increases the efficiency of X-ray production through Bremsstrahlung interactions. We will see that later. Second, tungsten has an extremely high melting point of almost 3000 degrees Celsius. This high melting point is very useful for X-ray tube because in X-ray tube there occurs intense amount of heat, and tungsten target can easily tolerate these extreme temperatures without melting, cracking or suffering any damage. This heavy copper block acts as an excellent thermal conductor. It is a very good conductor of heat. That means it rapidly draws this intense heat away from the tungsten target and safely transfer it to the outside water cooling system. This water cooling system keeps circulating cold water all the time to absorb this heat. Finally, notice the large electrical circuit connecting the cathode and the anode. This black thick wire. This provides the very high voltage needed to accelerate the electrons across the empty tube. So this is all about the entire setup of an X-ray tube and its various components. Now I'm going to show you how this X-ray tube functions to produce X-rays. First, look closely at the core component, cathode. This is cathode. You can clearly see a coiled golden color wire in it. This is the negative electrode, which we call the cathode. It is essentially a very simple tungsten filament. Notice how it is glowing bright orange in this animation. Can you see that? This happens when we pass a electrical current directly through this wire. The filament quickly heats up to an extremely high temperature. As this tungsten filaments get incredibly hot, the outer electrons of the tungsten atoms actually boil off the surface. We call this fundamental process thermo-ionic emission. Thermo means heat and ionic emission means releasing charged particles. This process gives us a ready cloud of free electrons to use. Now, please direct your attention to the right side of the screen. You can clearly see a large tilted metallic plate here. This is our positive electrode, which we call the anode. There is a specific area on this anode, what we call the target. In our upcoming slides, we will see exactly what happens when these free electrons travel across the gap and violently strike this target. Now, look at the metallic cylinder that completely surrounds this glowing filament. We commonly call this the focusing cup. In this specific setup, it is a molybdenum cylinder. You might ask, why do we need to surround the filament with this metal cup? Remember that we just boiled off a large cloud of free electrons. Electrons are seen as green dots here. Because all these electrons carry a negative electrical charge, they will have a natural tendency to repel each other. If we do nothing at this moment, this cloud of electrons will quickly spread out and scatter in all directions. We do not want that to happen. We need them to travel in one direction and hit a very specific and small area on anode target. To solve this problem, we keep this focusing cup at a strong negative voltage. This negative charge strongly repels the negative floating electrons from all sides. It forces them to stay tightly packed together right in the center of the cup. This simple design beautifully shapes our electron cloud into a very fine focused pencil beam. Now they are perfectly ready to aim at the target and waiting to be fired. Now it is time to put these stationary electrons into motion. How do we do it? To do this, we instantly apply a massive electrical voltage across the entire tube. You remember that large electrical circuit connecting the cathode and anode here? This provides a very high voltage needed across the empty tube to create a massive potential difference. This high voltage makes the cathode highly negative and the anode highly positive. Once again, this high voltage makes the cathode highly negative and the anode highly positive. Now remember a fundamental truth in physics. Opposite charges always attract each other. Here in X-ray tube, positive attracts negative. Because of this massive potential difference, the positive tungsten anode pulls the negative electrons towards it. The electrons are instantly forced to cross this empty vacuum chamber. Because there is a strict vacuum, they do not hit any air molecules along the way. They are continuously accelerated towards the target like tiny, high-speed bullets. Let us move to the next slide to watch them accelerating and travel across this empty glass towards anode. Watch this again. Let's watch it once more to be absolutely clear. You saw how electrons are created or generated by heating copper filament, concentrated in the center by negatively charged focusing cup made of molybdenum, forced to accumulate in the center as a pencil beam, move and accelerated towards positively charged tungsten anode and hit the target. Now see this collision between electron and tungsten anode from the front angle. Now see this collision from side very closely. Look at the exact moment of impact on your screen here. This tightly focused beam of electrons has finally smashed onto the heavy tungsten anode target. This sudden collision is where the real physics happens. What exactly happens in this collision of these electrons onto target? Listen very carefully now. When high-speed accelerating electrons are made to stop suddenly, they lose their entire kinetic energy. This kinetic energy is released and converted into some other form of energy. Over 99% of the kinetic energy from this massive collision is completely wasted as thermal energy, heat. Thermal energy, heat. The heat generated is so intense that we must use a rapidly spinning tungsten target, a heavy thick copper blocks, and this special cooling water circulating system to remove heat from the tube continuously all the time as long as the X-ray tube is on. What about remaining 1% of energy released? What happens to it? It is only this tiny 1% fraction of energy that is successfully converted into X-rays photons. X-ray photon. Once again, this tiny 1% fraction of energy is successfully converted into X-ray photons. This is the exact moment an X-ray photon is born. Once again, this is the exact moment an X-ray photon is born. X-ray photon is born now. This is the X-ray photon which will be used clinically to take chest X-ray or kill a cancer cell. Notice the bright blue rays emerging downwards from the tilted target in this image. These lines represents our actual X-ray photon beam. Because the target is specifically tilted at an angle, this beam is directed out of the tube like this. It safely exits through a small thin window in the glass envelope. This is a real image of X-ray tube, and this is that window from where this beam comes out like this. This is exactly how we harness the power of this radiation. The beam has now left the tube and traveling towards our patient for imaging purposes or therapeutic purposes. Friends, this is all about how X-ray tube and how X-rays are produced in an X-ray tube. Now I will show you how changing various parameters affect the production of X-ray. There are two distinct identities of any X-rays. One is quantity and the other is quality. See how to increase quantity of an X-ray. Quantity simply means the total number of X-rays or the intensity. See this bright blue X-rays. These blue rays are our final X-ray photons. X-ray photons. Look at the green fast-moving electrons emitting from cathode. This continuous stream of moving electrons is what we call the tube current. Tube current. We measure this tube current in milliamperes or simply MA. The total number of electrons striking the target directly decides the intensity of our X-ray beam. Once again, the total number of electrons striking the target directly decide the intensity of our X-ray beam. If we want to produce a higher quantity of X-rays, we simply need to fire more electrons. How do we do that? We do that by simply increasing the electrical current flowing through the cathode filament. Just increase the current. What happens when you increase the current? This makes the filament hotter and boils off a much larger cloud of free electrons. More electrons hitting the target will directly produce a higher intensity of X-rays. This simple relationship between tube current and beam intensity is essential for your clinical practice. Now look at the quality of X-ray. How to increase quality of an X-ray beam? See this bright blue X-rays. These blue X-rays are our final X-ray photons. This is the actual radiation beam that successfully exits the machine. We generally describe this exit beam using two very important terms. The first term is the quantity, which simply means the total number of X-rays or the intensity. As we just discussed, we can easily increase this quantity by simply increasing the tube current. The second term is quality. Quality tells us what is the actual penetrating power of the beam. How to increase this quality? To increase the quality, we must increase the high voltage across the tube. Increase the voltage. When we apply a higher kilovoltage, we create more massive potential difference between cathode and anode. This forces the electrons to travel much faster across the tube. These faster electrons will then give birth to much stronger, highly penetrating X-rays. That means high quality X-ray. This simple relationship is the absolute core of our treatment planning. In our daily clinical practice, you will constantly use these exact principles to control both the quantity and the quality of your radiation beam. Now, of course, when you are asked in exam or viva about the X-ray tube and X-ray production, you won't be able to draw these animations I showed you. This is the diagram you will draw for your X-ray tube. Explain every part of this X-ray tube and its importance. You show the envelope, which is air evacuated, cathode, electron stream, tungsten anode, and the X-ray beam emitting finally. So guys, with this I finish my today's lecture on X-ray tube and X-ray production. It is extremely important that you understand it and make a solid foundation for your further radiation physics. So guys, this brings us to the final and closing slide of today's presentation. We have just seen the X-ray tube in detail. We saw the generation of electrons at the heated cathode. We saw their acceleration across the vacuum. And we analyzed their deceleration upon striking the heavy tungsten target. We established a very important physical fact. Over 99% of the kinetic energy from this collision is converted into heat. This energy is entirely wasted. Less than 1% of the energy survives. It is only this tiny 1% X-ray which forms our clinical X-ray photons. Here comes the next topic. I will teach you in my next lecture. How actually is the radiation formed at atomic level when the high speed electron hit tungsten target? how do these high-speed electrons interact with the atom of the tungsten anode target right here and produce X-ray photons? Two interactions occur here. First, Bremsstrahlung X-ray radiation production, and second, characteristic X-ray radiation production. These two terms, Bremsstrahlung and characteristics, describe the specific atomic interactions that create our clinical X-ray beam. Listen, in a therapeutic megavoltage beam we commonly use in our linear accelerators, characteristic radiation makes less than 3% of total X-ray photons. This means that almost 97% of clinical X-ray beam is made up of Bremsstrahlung radiation. In our next lecture, we will look deep inside these two specific atomic interactions in detail. Be careful, don't get confused these two types of interaction with those three types of interactions such as photoelectric effect, Compton effect and paid production of effect of radiation with matters. Those interactions occur later when the clinically used X-ray beam hit the body and interact with body. I will teach you those three interactions in separate lecture later. In our next class, we will look at the exact moment the electron strikes the tungsten atom here. We will learn how a high-speed electron interaction near the nucleus provides Bremsstrahlung radiation. We will also learn how the ejection of an inner shell electron produces characteristic radiation. Understanding these two physical processes is essential for your understanding of radiation physics. I encourage you to understand today's class on the X-ray tube before our next class. Thank you for watching. I will see you in next video. Signing off, Parveen Ehlawat.